this lecture, we look at the properties of light sources. Most shading calculations require the direction from the point on the surface to the light source position. As we move across a surface calculating the intensity at each point, we should recompute this vector repeatedly. However, if the light source is far from the surface, the vector does not change much as we move from point to point. The calculations for distant light sources are similar to the calculations for parallel projections. They replace the location of the light source with the direction of the light source. Notice the location has been changed with the direction, so we get from a point representation to a vector representation. The intensity of light that reaches the surface of an object is inversely proportional to the distance between them. That is, the light should get attenuated with 1 over d square. However, this will create dramatic drops in light intensities, and to cater for that, we can add a factor of 1 over a plus bd plus cd square, a quadratic term, to attenuate diffuse and specular light sources from point light sources and spotlights. The terms a, which is a constant term, and the linear term bd will soften the effect of the point light source. Note that the distance term is not applied to the ambient term. This is because ambient light does not have a location. It is present everywhere in the scene. Now recall the Phong lighting model that we studied in the previous lecture. It has three terms: diffuse, specular, and ambient, and it uses 4 vectors to calculate how light is reflected from a point P. Look at shading from the light source point of view. In the Phong model, we add shading results from all light sources together. Each light source has separate diffuse, specular, and ambient terms to allow for maximum flexibility, even though this form does not have a physical justification. Each term has its own red, green, and blue components. Hence, there are 9 coefficients in total for each point light source. The diffuse red, diffuse green, diffuse blue, the specular red, specular green, specular blue, the ambient red, ambient green, and ambient blue component. Even though the ambient component of light does not have a specific location, we add an ambient component for each light source to model how this light source contributes to the global lighting effect in an ambient fashion. Replace these 9 coefficients by a 3 by 3 illumination matrix for each ith light source, where every column corresponds to a different color component, such as red, green, and blue, and every row corresponds to a different component of the light in terms of ambient, diffuse, and specular. In practice, we will use constructs such as vector 3 light I ambient, light I diffuse, light I specular, where I could be a number such as light 1, light 2, light 3, and we will define 3 different vectors to represent their ambient, diffuse, and specular components. Or we can use vector 4, and we will study later where the 4th component is for. At the reflection part of the shading, we construct the reflection model by assuming that we can compute how much of each of the incident lights is reflected at the point of interest. For example, for a red and diffuse term from light source I, we can compute the reflection term RIRD, and this multiplied with the diffuse term of the light source I in the red light will give us the reflected red light. And to get the overall red reflected light, we can add the ambient, the diffuse, and the specular term. And these reflected lights can be represented by a 3 by 3 matrix in a similar way represented the light source components. To get an overall red reflection, we'll have to add all the diffuse, ambient, and specular components of all the light sources, so hence a summation over here. And finally, we add the overall global ambient term in the red light to this to get the final red illumination. We can derive the final illumination in all three colors by adding up the ambient, diffuse and specular components of the reflected light.